This video focuses on the Fault Reporter class and related classes. We referred to the Fault Reporter class in several places, primarily in the various videos about the example subsystems. The Fault Reporter class has really two responsibilities. Um, it originally came from or is inspired by Team 3015's Advanced Subsystem Abstract class, but it has evolved a bit since then. Um, The first responsibility is that the fault reporter checks for and generates alerts for faults on devices. It uh, only checks for faults when the robot is disabled, and it does so at 1 second intervals. There is a command that will force a check for faults when the robot is enabled. Perhaps that could be done if something appears to be quite wrong and the driver and operator aren't quite sure what, and they need more information to try to recover during a match. Um, the second thing that it does is it manages system checks for subsystems. And we saw each subsystem calling the register system check method on the fault reporter to register their system check. And we'll see a little bit about how that works and how those are reported as well. A lot of that stuff ends up being published or logged via Advantage Kit and published some in network tables as well, to a degree. So let's see, what do we really want to? So both of those responsibilities are within the same class, which can be a little bit confusing, but that's okay. It is a singleton, so it has a get instance method like we're familiar with. Let's focus on the system check functionality first. So we saw the subsystems invoking this method, register system check. And so what this does, is it keeps track of faults while running the system check. And it does that by wrapping the command, the system check command provided, passed as a argument to this function. It wraps it in some more stuff to help this out. So let me show you. Here's the wrapped system check command. So what it does is it does some housekeeping first. And so you'll see that it logs that the check ran and sets that to false. So it's like we have not run the check. It clears all the faults for this subsystem. So we're starting with a clean slate. Then it runs a provided system check command. And after that completes, it then checks for faults. Um, and it logs the status that it gets, um, and whether the system is okay is a Boolean, just because if the system status is okay, we know that's the case, and that the check ran to false. So all of this gets logged at the end of the system check. It names the wrap system check command with a subsystem and a check. It puts it into Smart Dashboard as a command. This makes it easy in one of the tabs in the Elastic Dashboard, for example, to add this so that that button can be pressed in the pit to run the system check on the given subsystem. Yeah. So that's how system checks work. Other things that Fault Reporter does is it logs or it registers some other dashboard commands as well that can be put into a tab in Elastic Dashboard that might be useful. One is the clear all faults command. So that goes in the dashboard. Here's what the command looks like. Basically, what it does is it goes through every device that is registered with Fault Reporter and clears all the sticky faults. And then it clears out any of the alerts that are active, sets them all to false, clears the list of faults and alerts for the subsystem as well. So basically, it's just clearing everything out. This is part of our um, pre-match checklist, is to clear all faults in this manner, and this automates that process for us. We want to do that because when the robot comes back after a match and we're looking to see if there are any sticky faults, we want to make sure that we know that that sticky fault occurred during the match that just played and isn't left over from matches ago or days ago or months ago. So that's why we clear all faults. We also put on the smart dashboard a check for faults button um, that will um, force the fault reporter to check for faults even if the robot is enabled, as I referred to earlier. Set up callback here. Here's where we schedule to check for faults when disabled. That runs every 1 second. That's a command that will check in the background. A lot of the rest of the code here is just keeping track of all the things. So adding faults for a given subsystem. Here's the add fault method that would be called within system tests. We saw that in the various subsystems, this one or this one. Being able to get the faults, we saw that in the systems test, so we know when to stop. These are all used internally. All right, so that's all the system test stuff. The next public method here is register hardware. We saw this method called within each example subsystem in the hardware specific classes. So this is where each device, motor, encoder, things like that, pigeon, would be registered with the fault reporter. And we give it a subsystem name, we give it a label, we give it a reference, in this case to, this is a Talon FX device. You'll notice there are register hardware methods for every different type of device. So a Talon FX, PWM motor controller, Spark Max, pigeon, camcoder, all of those. And they're all implemented in a fairly similar way. They're overridden because um, the checking has to be done in a different way. So for example, with the um, Talon FX, we are going to create a new self-checking Phoenix motor object that is responsible for checking for faults on the Talon FX, and we'll see that in a moment. This is a little bit of code that was added as a workaround with the Canivore. I don't know if that is still required. This is a couple of years old, and CTRE said this was what should be done so that hoot files are properly generated. I don't know if that's still the case, but we still have it here. So anyway, so this creates that new self-checking Phoenix motor. So self-checking is a interface that basically just has a check for faults method. And there's a clear sticky faults method that needs to be implemented for classes that implement the self-checking interface. So as you can see, there's one of these for camcoders, Phoenix motors, pigeons, PWM motors, Spark Max. Let's just look at the Phoenix motor one as an example. So you can see a little bit of what it does. One thing I want to be clear about is that these classes do not check for every possible fault, only for those faults that we feel we want to be alerted for, which is most of them. But for example, one notable exception is when a current limit is hit, which happens essentially all the time or quite frequently. We don't want alerts to be generated for that. We don't want that to that noise to be as part of this data. And so we don't check for whether we're hitting current limits or not. But what you can see is the things we do check for here. So these are all sorts of different faults that we check on a Talon FX device. And there's a lot of them. And then we also check for all the sticky faults, the corresponding sticky faults for all of them, and log that as well. We also have a debouncer here that we use elsewhere within 3061 lib that checks to see if the device is okay or unreachable. Again, maybe it drops off for a brief moment, but with our debouncer, we only want to generate that alert if it's gone for half a second. There's still quite a bit of time. And then the method here to clear the sticky faults. So that's what we've got here within the specific class. So going back to fault reporter. Um, we have all the different register hardware methods that are done, and that takes care of that. Here's the check for faults when disabled method that we schedule. Only if we're disabled do we run the check for faults method. And the check for faults method simply iterates through every subsystem, and then goes through each device registered with that subsystem, um, and on each device checks for faults and then adds that fault as needed, which will generate the alert. Um, the reason why we only do this when things are disabled is because there's a performance hit for checking all of these things on all of these devices. So we only want to take that hit when the robot is disabled. And also, if a fault is generated in the middle of the match, it's unlikely the driver or operator can do anything productive with that information, but we can certainly capture it and analyze it later. So that is the fault reporter and associated classes.